This is a hypotrochoid, aka a math tool for math students to make art without really knowing anything about art. With the drawback that sometimes the art that it makes is actually just 100% math and 0% art.
Wait, it's just an ellipse.
Nevertheless, it's still plenty interesting on its own merits. For this exploration, we'll be starting with nothing but the Wikipedia description of the hypotrochoid, which is a lot less insightful than I expected, which means that we'll probably have to do a lot of original thinking on our own. And we'll work our way up from there to understanding what the hypotrochoid is and why it works the way that it does. First, what is a hypotrochoid? Well, we'll start with a stationary circle, and then add another circle that rolls around on its inner circumference, like so. The rolling circle has an arm that extends out from the center, and a pen is located at the tip of the arm. As the circle rolls, the arm also rotates, and the pen traces out a curve. This curve is called a hypotrochoid. If you're familiar with the spirograph, then the hypotrochoid probably already looks familiar to you. Indeed, one of the many shapes a spirograph can draw is a hypotrochoid. But is there a way to know before drawing what the hypotrochoid drawing actually looks like? The answer is yes. By looking at the sizes of the circles and the length of the arm, we can deduce the general shape of the hypotrochoid drawing. How we can do that is a question we'll be attempting to answer today. First, some notation. We'll let capital R be the radius of the stationary circle, and lowercase r be the radius of the rolling circle. The length of the arm will be denoted as d. For convenience, I'll just refer to capital R as big R and lowercase r as small r. For our experiment, we'll be varying the ratio of small r to big R, and observing the resulting shape of the hypotrochoid. For now, we'll keep d fixed and just observe what happens as the ratio of small r to big R changes. Just some preliminary notes. We'll simplify the ratio to its simplest form, because equivalent ratios of small r to big R yields the same shape, just on different scales. Here are the first couple of observations. Let's start with the ratio of 1/2. Here we just have an ellipse. For a ratio of 1/3 and 2/3, we see that for both of these our shape has 3 lobes, for lack of a better term. By lobes, what I mean is this shape that's reminiscent of a flower petal, or sometimes it might look like these sharper corners. Next, for 1/4 and 3/4, we have 4 lobes. For 1/5 through 4/5, we have 5 lobes. And finally, for 1/6 and 5/6, we have 6 lobes. Can you identify the pattern here? Note that some ratios are missing because when we simplify them, they overlap with the previous ratio. For example, 2/4 would be the same as 1/2. Next, we want to know how many revolutions the inner circle makes before completing the hypotrochoid drawing. By revolution, I mean how many full laps around the larger circle does the smaller circle make. So when the smaller circle comes back to the right side of the larger circle, it completes 1 lap, regardless of how many times it's rotating. So for example, this would make 1 revolution, and this would be another revolution. When we say the hypotrochoid is completed, we mean that the inner circle cycles back to its starting configuration, both in terms of position as well as rotational orientation. So basically, the drawing is done when the configuration looks like this again. If we just count, we see that for a ratio of 1/3, it makes 1 full revolution. For 1/4, 1/5, and 1/6, we have the same result. 1 full revolution. For 2/3 and 2/5, it makes 2 revolutions. For 3/4 and 3/5, 2, 3 revolutions. For 4/5, we have 4 revolutions. And finally, for 5/6, we have 5 revolutions. What's the pattern here? It seems pretty clear that both of our observations has an underlying pattern. That is, the number of lobes equals the number in the denominator, and the number of revolutions equals the number in the numerator of the ratio. So for a hypotrochoid where small r over big R simplifies to a over b, we have b lobes and a revolutions. This will be our hypothesis. As with any good experiment, we will verify our hypothesis, but in our case, using mathematical reasoning. But before we do that, we first address the elephant in the room. What is the equation of our hypotrochoid drawing? In our case, it's much easier to describe a hypotrochoid with a parametric equation, which is an equation describing the x and y coordinates of the curve with respect to some third variable. In our case, the third variable will be theta, which is this angle, the angle of the line connecting the centers of the two circles. Instead of deriving the equation from scratch, I think it's more insightful to see the final result and figure out how we get to the final result. From Wikipedia, we have this parametric equation. It looks kind of complicated, but like always, we can simplify it and break it down into smaller, more manageable parts. We can see that the hypotrochoid is separated into two components. First, we have the circle that rolls around inside the stationary circle. And second, we have the arm that rotates as the smaller circle rolls. The first term in our equation tells us the x and y coordinates of the center of the smaller circle. Using basic trigonometry, we can verify this. The x coordinate will just be the radius, big R minus small r, times cosine theta. Similarly, the y coordinate will be big R minus r times sine theta. The second term accounts for the additional x and y components due to the arm. And like before, the x and y coordinates are just the radius, which is d, times the cosine or sine of an angle. But in this case, the angle isn't theta. It's this angle phi that the smaller circle makes as it rotates around itself. To figure out how to calculate phi based on theta, we need one key insight. That is, the distance a smaller circle rotates is equal to the arc traced out by the center of the same circle. You can intuitively see this by imagining a paint roller. The distance that you push the paint roller is the same distance that it rolls. The distance that you push it is the same distance that the center moves, which is this arc. And the distance that it rolls is the same as the arc length that the circle goes through as it rotates, which is this arc. If we recall that the arc length is the angle theta in radians multiplied by the radius r of the circle, we have this equation. The arc traced out by the center of the circle will be big R minus small r times theta, and the distance a smaller circle rotates is the arc length traced out by the circle, which is r times phi, the right-hand side. And then we'll just solve for phi to get phi is equal to big R minus small r divided by small r times theta. But since the arm rotates in the opposite direction that the circle rolls, we have to use negative phi. If you substitute this in to d cosine and sine phi, we get the second term of our parametric equation. And combining that with our first term, we have the complete parametric equation. Now we move on to deriving the number of revolutions. Remember that our hypothesis is the number of revolutions is equal to the number in the numerator. So if small r over big R is already in its simplest form, we expect the number of revolutions to just be small r. We need to notice two things first. The first one is that theta has to be a multiple of 2 pi radians when the hypotrochoid is completed, because the smaller circle needs to be exactly on this right side of the larger circle. If theta isn't a multiple of 2 pi radians, we could have an overshoot or an undershoot. In fact, if n is a number of revolutions, then theta has to be exactly 2 pi times n. Since 2 pi radians corresponds to 1 revolution, we have n revolutions corresponds to 2 pi n radians. Next, we notice that phi is also a multiple of 2 pi. This is because the rotation of the smaller circle needs to be the same as in the beginning. meaning that it has to have completed its rotation around itself. If phi wasn't a multiple of 2 pi, we would also have an over rotation or an under rotation. From our previous derivation, we have these two equations. Plugging in theta, we have phi is equal to 2 times pi times big R minus small r over small r times n, which simplifies to this equation. Since we want phi to be a multiple of 2 pi, we simply need this term to be an integer. N is already an integer, so what we really need is for big R over small r times n to be an integer. If big R over small r is already in its simplest form, then n will just be small r, which is the same as in our hypothesis. Next, we move on to the number of lobes. We hypothesize that the number of lobes will be equal to the denominator of our ratio, which means that if small r over big R is already in its simplest form, the number of lobes is just big R. First, let's figure out why these lobes are even here in the first place. If we rewatch the animation, we can notice some patterns. Each lobe is formed when the curve is farthest away from the center of the stationary circle. These maxima form the tip of each lobe, and the number of tips of the lobes is equal to the number of lobes itself. These maxima occur when the radius of the large circle and the arm of the small circle are perfectly aligned in the same direction. You can think of this as follows. Let's label the distance of the curve from the center of the large circle as L. When the radius, big R, and the arm D are perfectly aligned, the curve is a distance of R plus D away from the center. So L equals R plus D. But anywhere else this can't be the case, because the radius and the arm together with L forms a triangle, and we know that the sum of two sides of a triangle is always greater than the length of the third side. Hence, L is always less than R plus D. When the condition for the maxima is satisfied, that the radius and the arm are aligned in the same direction, observe that the arm is perpendicular to the tangent line at that point. This is due to a circle theorem which states that the radius drawn from the center to a point on the circle is always perpendicular to the tangent line drawn at that point. Since the arm points in the same direction as the radius, it too must be perpendicular to that tangent line. Now we have all the pieces we need. Let's unwrap the circle into a straight line. As the smaller circle rolls on this unwrapped circle, we see that the arm is perpendicular to the unwrapped circle at these positions. But notice that these are exactly the positions where the smaller circle makes a full turn on the unwrapped circle. So what we really want to count is how many times the small circle makes a full rotation as it rolls around the unwrapped circle. This is just going to be the length of the unwrapped circle, which is its circumference, which is 2 pi times big R, divided by the circumference of the smaller circle, which is 2 pi times small r. But remember that this is a number of rotations as the smaller circle rolls around the larger circle once. We know that it actually makes r revolutions, so it goes around the larger circle small r times. So we have to multiply our result by small r. After cancellation, we have the number of maxima equals big R, which is equal to the number of lobes, which confirms our hypothesis. Now that we've seen the relation of the ratio of small r to big R to the shape of the hypotrochoid, let's figure out as an example what ratio we should use in order to create this flower hypotrochoid pattern. Since we have many lobes, we'd want big R to have a larger value, for example 13. And since we want the hypotrochoid to look more rounded, we'd prefer small r to have a lower value. This is because the smaller the value of small r, the lower the relative speed of rotation. And the lower the relative speed of rotation, the more gradually the hypotrochoid changes its shape. And the more gradually it changes its shape, the rounder it gets. Using this ratio, we can see that the hypotrochoid does indeed draw a shape that is similar to the flower pattern we wanted. So this is getting a bit long, but we're finally at the end. Just some final comments. The length of the RMD determines how much the curve collapses in on itself. A large value of D makes a hypotrochoid look bloated and round, and a small value of D causes a hypotrochoid to almost collapse in on itself. The special case of D equals small r just results in sharp corners. Finally, I was a bit curious about what would happen if small r happened to be bigger than big R. And in this case, we just have some familiar polar curves. The derivation is pretty straightforward but tedious. You just basically plug in the ratio of small r to big R into our parametric equation, and we get some corresponding polar curves parametric equation. Thank you for joining me on this long exploration, and I hope we both learned something new today.